So I'm going to be continuing the theme, I suppose, of using MEMS resonators as mass balances for impactors. But I'm going to be coming from a slightly different approach. So I'm a PhD student within the Center for Atmospheric Science in the University of Cambridge. So I'm more approaching it directly from the application side. So hopefully there's a bit of a nice contrast between the two talks. But instead of a traditional outline, I'm going to be giving more of the objective on the really broad standpoint. So just we want to be able to collect particles onto a resonator and hopefully be able to detect mass. And this objective essentially acts as my outline. So I'll talk about why we're collecting particles, and this is going to be some overlap between the previous talk and also how we're collecting particles and why we want to use resonators, which type of resonators we're using, and finally, hopefully I can show we're detecting mass. And then since I work with atmospheric scientists, I do get some additional questions and some actually overlapping from the previous talk in terms of how long can we use these before we either have to clean them or throw them out. And also, can we get any additional information in terms of the aerosol composition directly? But starting off with the doom and gloom, as we just heard, there's quite a few health effects associated with particles in terms of we breathe them in and they transfer into our bloodstream, and then they can lead on to things like heart attacks, etc. But the other one I'll just touch on, since we didn't really feature it in the last talk, is just the environmental effects. And traditionally, aerosol particles in the environment have a cooling effect rather than the usual greenhouse heating that you hear about. So you may have heard of geoengineering projects with aerosols. The idea is to send particles into the atmosphere and reflect sunlight. So there's some interest there from particle counting, but the real interest is in having a smaller time scale for measuring rather short lifetimes. So a lot of particles react very quickly, either to grow into larger particles or to go back into the gas phase. So there's a strong push for higher temporal resolution. And at the moment, there's a lot of use of the optical particle counters because they serve their purpose quite well because they can count particles individually and size them. But they have this major limitation of not being able to size below 300 nanometers, which is the size that really leads to health effects and also is associated with the short-lived aerosol products in the environment. And then the other side are the impactors. And they are quite classically used within the environmental standpoint as well as pharmaceuticals. But their main limitation is that you need to use filter measurements that usually last for about an hour plus, so you lose any of that time resolution that you'd like. And so that's kind of where the resonators come into play, where we'd hope they have a high sensitivity so we can measure those small particles, and they also give us the time resolution we'd like. And this all kind of started back in the 80s when I think this is the first impactor that kind of switched out the filters, and instead they replaced with QCMs. So now now there's more and more work with MEMS resonators kind of replacing the QCM idea. There are also other groups that do Faraday cups instead of the filters. So they're all kind of acting on the same idea. Now I'm just going to touch on the operating principles again. We obviously just saw these, but in a really broad sense, the resonators are as the mass sensor, and the idea is that if we increase mass, so if we're just adding particles to its surface, we should see negative frequency shift. There are a couple caveats I'm not going to go into right now, just from a sense of time aspect. But then for the impactor, we saw how they're basically you use a nozzle to accelerate particles to collide with your target, so in my case, a resonator. But there are a couple caveats, and I do want to just touch on this particle range entrainment as it just came up earlier. That's the idea that if you're sending particles towards your surface, there's a decent chance that some of those particles will bounce off and go and continue on in the airflow, or a particle will hit one that's already attached, and then that will then peel it off, and you'll lose mass that way. So if you have a cascade arrangement, which just means you have several impaction stages after each other, you'll actually skew your particle distribution with that. Now the resonators I'm using, I'm not going to go into too much detail. If you'd like more detail, I'll point you towards this paper that uses the exact same design. But they are piezoelectric bulk acoustic mode resonators, and they're relatively large. They're 1.4 by 1.4 millimeters. And for this study, I'm really just looking at the square extensional mode, which is an in-plane mode characterized by the uniform contraction and expansion of the plate. From the experimental setup, which is really my focus, because I want to be able to test and characterize the different responses from the aerosol particles and the resonators. It's a relatively simple idea. So we have particles, and we send them towards a DMA, which is a differential mobility analyzer. And I apologize ahead of time for all the acronyms. But this is used to size particles. So it's based on the electric mobility of your aerosol. And then you get a monodisperse distribution out. So you can pretty much produce any type of particles you'd like and size, only take a specific size to send towards your impactor. So the impactor here is just what I've labeled as an MIS, and the entire flow is being driven by a vacuum pump. And then we have two CPCs, which are condensation particle counters, which are just modified optical particle counters that can count smaller particles, just because of the condensation of butanol onto those particles. And those provide per second resolution particle concentrations. So I have a concentration before and after my impactor. So this is that impactor stage. It's quite large, especially compared to Maribel's. But the main point here is to have something that we can switch lots of different components out. So at the 18 by 18 centimeter size, it is large, but we can put essentially any chip into the socket and access any resonator on that chip. So if we want to test different types of topologies, we can do that quite easily. And it also serves a way of aligning. So we have these two axes to align the resonator underneath the nozzle. And then if we put the lid on the nozzle here, we can switch out as well. So we can change the number of jets and the size of those jets. And then this actually is essentially a screw holder. So we have some separation alignment just based on the pitch of that screw. For all the tests we'll be talking about today, though, I'm using a nozzle that has 3 by 0.25 millimeter jets. So at a flow rate of about 1 liter per minute, this should cut off around 300 nanometers. So for the experiments I want to show, I did 2 different types of particles. So for one, we did polystyrene latex, which is a very common solid particle sizing standard for calibration purposes. And then the second is one that people may not be as aware of, is an α-pinene secondary organic aerosol. I'll be referring to that as SOA for most of the talk. But this is a highly viscous liquid aerosol particle, and it's quite commonly used in environmental studies. So that's also why we're looking at it. But for all the tests, we're size selecting 300 nanometer particles, so it's always the same size originally. And we're collecting particles for at least 1 hour. And throughout the process, we're measuring temperature, relative humidity, and the particle concentrations. The temperature RH measurements are inside that impactor stage, but they're in a bit of a dead volume. So it's not measuring directly from the flow, but it's measuring the ambient conditions. So moving on to the results, I figured I'd start by just showing kind of how we get our numbers out of this. So on the left here is all the information we get from the box, so to speak. So on the top is temperature RH. I'm not going to go into it too much, but I'll just point out that we didn't do any temperature correction yet, just because the effect of that temperature is much lower in magnitude than the effect of the mass we're adding. And then the bottom, you can see the frequency shift in black during this collection period, and then you can also see a slight drop in quality factor. So the idea is that we want to compare this information to those CPC concentrations. So on the right here is our CPC upstream and CPC downstream, and as you expect, there's a drop. So we're making the assumption that that difference is consisting of all the particles that have been collected onto our resonator. And this is not necessarily true because we're neglecting any diffusional losses within the relatively large volume and any coagulation losses and things like that, as well as the actual any alignment issues on the resonator as well. But if we make that assumption and we take the difference between those two concentrations, we can integrate over time during our collection period, and we can get plots like this, which give us our mass collected over time. So from the CPC derived, which I was just describing in black, and then we have the frequency derived in blue, which is taking this frequency shift and multiplying it by the theoretical sensitivity, which is on the order of about 28 hertz per nanogram. And so we get a decent correlation. You might be thinking this is a bit too good, and that is partially true. There's an additional scaling factor used, and for all the results I'll be showing that it ranges from about 5 to 10, and this is going to be accounting for those diffusion coagulation losses, and also some of the effects of the different types of aerosol as well. So we did a few different tests, and I'm not going to go into too much detail about each of these, but the basic idea I want to highlight is we can test different types of aerosol, so the solid and the liquid particles, and different concentrations. So relatively low 3,000 particles, and then quite high at 35,000 particles per cubic centimeter. And just as a reference, kind of ambient particle concentrations for sizes from 100 nanometers to 3,000 nanometers is on the order of 3,000 particles per cc. So these are very highly elevated levels. But the idea for doing this is that we wanted to know what that saturation limit is. So how long can we run this for before we need to really start worrying about the calibration issues. But before I get to that, I'm just going to touch on what these look like afterwards. So we could take some optical images of these surfaces afterwards. So all the collection is done on the back to protect the wire bonds and the electrodes. But just to highlight a couple things, one is you can quite clearly see the difference, the effect of the difference in concentration, and you can see the liquid aspect of this SOA, so you can see the interference fringes from the thin film. The other thing I just want to touch on is at the beginning I mentioned that we had three jets in the nozzle, and it only looks like we're collecting by 2. The most likely scenario here is just that that third nozzle got clogged during those tests. So unfortunately, we should be expecting a third pile of PSL particles here. Okay, so now moving on to that question that I get asked the most, which is how much can we collect? And in order to do this, we used an even higher concentration of SOA particles and ran it for 4 hours. So this is much longer collection time. And if we just initially look at the frequency shift itself, you don't necessarily see anything. But then if we do the same type of integration versus just a straight linear multiplication of the frequency shift, we get something like this. So it's sort of implying that maybe after 100 minutes of collection that we are getting some deviation from the expected, and that might be that start of the saturation point. The expectation is that if we run this for even longer, the frequency shift should just level off and stop changing as any additional mass just isn't being registered by the resonator. But then you'll also notice that there is this essentially leveling off of the Q factor, and there's potential that those might be related. This really does require a bit more further repetition, but they don't quite line up. But hopefully if we repeat this a few different times with the same type of particle and then vary it with the solid PSL particles, we should hopefully see some differences there. This is the final image, and you can really see compared to the previous SOA image how much we collected. So this is 40 micrograms, which from an environmental standpoint that is quite excessive. So in terms of the lifetime, this is quite hopeful, because we can obviously lower the flow rate and extend the lifetime of these devices as well. And then the second question I quite often get is what other information we can get. And this is a work done with help from a postdoc in my group, Dr. Chiara Gioia. And this is using liquid extraction surface analysis mass spectrometry, which is essentially taking a solvent and you touch it against your surface, and any material on that surface that's soluble within that solvent will get absorbed, and you pull that solvent back and then you put it into a mass spectrometer. And then from there you can get the chemical composition. So you can see we did 4 repeats because you can see the residual coffee ring stains, and then we get this composition. And I'm not expecting too many people to really be familiar with these, but the basic idea is that we can compare this chemical composition to the expected chemical composition from the reaction to produce the SOA that we did. So that's a reaction of α-pinene and ozone, which is a very commonly studied reaction. So we know what we're expecting to get, and luckily we got exactly that. So this is kind of a relatively simple just proof of principle, but the idea is if we take this out into the ambient, we can get a good idea of the ambient chemical composition as well as the mass distributions. And with that, I'm just going to conclude. So we have a new setup that allows us to test different resonators and different particles, and there's lots of different things we can play with in terms of adjusting the relative humidity and looking at the collection efficiency of the device. We've shown that the LISA MS system can actually work with resonators to analyze the chemical composition, and we've maybe seen an initial step at actually being able to quantify the saturation limit for particle collection of these types of resonators. And with that, I'd like to thank you for your attention, and I'm happy to answer any questions.